Alexander Leonidovich Skubachevskii. 1 minute for Jürgen Batt and Anna Jorn.
Что нет, никак.
The minute is over, so let us start our lecture of Jürgen Batt, Anna Jorn, and Alexander Leonidovich Skubachevskii, stationary spherically symmetric solutions of the Vlasov-Poisson system depending on local energy. Please.
Thank you. This lecture is based on our joint work with my German friends, Professor Jürgen Batt and Anna Jorn. It's connected with a problem arising in astrophysics, in particular is in so-called stellar dynamics. Let me tell you that usually experts in astrophysics, when they can measure brightness of gravitating matter in space, they can calculate local density. But another important problem, if we know local density of gravitating matter, how can we find Newtonian potential? So, roughly speaking, this is the aim of this lecture. As it is well known, gravitating matter for particles in our outer space can be described with the help of so-called Vlasov-Poisson equations. We want to find stationary solutions, therefore we consider stationary Vlasov-Poisson system arising in stellar dynamics. It has the form 1, 2, 3. Here, F is the distribution function of gravitating matter, rho is the local density, and U is Newtonian potential. And here, X, V are space velocity coordinates. Clearly, if we integrate distribution function over all velocities, we obtain local density of gravitating matter. Equation 2, well-known Poisson equation, described dependence of Newtonian potential from local density. And the first equation, this is well-known Vlasov equation. Triple of functions f, rho, u, which is a solution of a Vlasov-Poisson system, is called spherically symmetric if this triple is invariant with respect to orthogonal transformations of coordinates. And of course, if we consider spherically symmetric solutions, we assume that this triple depends only on spherical radius r, which is equal to modulo x, and modulo of velocity v. It were a lot of papers which were devoted to stationary solutions. One can find review in our paper, which will be published in September in Journal of Computational Mathematics and Mathematical Physics. Let me only mention papers, of course, of my co-author Jürgen Batt, and papers which are also well known of Victor Valentinovich Votiakova, who is here. By the way, when I began to study Vlasov-Poisson equations, I used his available advice. In this lecture, we consider the following problem. For a given function p, we obtain sufficient conditions for p to be extendable. What does it mean? This means that there exists a stationary spherically symmetric solution f rho u of the Vlasov-Poisson system with f distribution function depending on the local energy given by the following formula, such that rho, the second coordinate of this vector function, equals to p. It's well known that for any rho from the Hilbert space C sigma, such that support of rho belongs to some ball of radius r, there is a unique solution U capital from Hilbert space C 2 plus sigma, for which U of x tends to 0 as x tends to infinity. Moreover, this Newtonian potential can be expressed by the formula 4. Let us consider the Newtonian potential U in the case of spherical symmetry. In this case, we can simplify the above mentioned formula for U. Sorry. Generally speaking, we assume that local density can have singularity at a point 0. From physical point of view, this is natural. And let us denote by C sub r the following set of functions from the space C from R plus, such that such functions are positive on some interval 0r and are equal to 0 for r greater than r capital, and the following integral converges. Let me remind that p can have singularity at 0. We define the operator L on this set. Clearly, this is not linear subspace. On the set C sub r by the formula 5. First, we shall consider properties of this expression LP given by 5. Lemma 1, let P belongs to C sub R and let rho belongs to C of R3 minus 0. Be spherically symmetric function such that rho of x equals to P of x modular for x non-trivial. Then the function U given by 4 Newtonian potential is spherically symmetric and has the following form: U of x equals to minus LP of R. So LP of R with minus can express Newtonian potential. Now denote by D sub R of L the set of all P from this set C sub R, such that P is strictly decreasing on the interval 0R. Lemma 2. Let P belong to D sub R of L, then LP is 2 times continuously differentiable on half axis, and its derivatives can be calculated by formula 6 and 7. It's clear. If in addition P belongs to C from R plus bar, so on the closed semi-axis, then LP belongs to C2 of R plus bar. So if P is continuously differentiable on the closure of half axis, then LP is 2 times continuously differentiable on closure of some semi-axis. Property 2, LP is strictly decreasing on semi-axis and has strictly decreasing inverse, LP minus 1. From lemmas 1 and 2 follows that if P belongs to D sub R of L, intersection with C, closure of R plus, so it is continuous on the closure of sub-axis, then there exists a unique spherically symmetric solution U of X, Newtonian potential, which is 2 times continuously differentiable with respect to R, of equation 2, such that U of X belongs to 0 as X by modular tends to infinity. Often we shall use this expression LP by P capital. Let me mention that in the case of spherical symmetry, we must have obligatory rho from Hölder space. It's sufficient to have continuous function in order to obtain solution of this equation, unlike general case. Now definition 1. A triple f rho u of functions f rho and u depending on r and u is called a stationary spherically symmetric E-dependent solution of the Vlasov Poisson system 1-3 if rho belongs to D sub r and there exists a function q such that the following properties are satisfied. So what does it mean function q? This is locally integrable function such that it is equal to 0 for non-positive values of s. It is positive on the following open interval. Then our distribution function has a form q, this function, depending on minus local energy minus some constant E0. Then, of course, U of R is equal to minus L rho. We have proved this before. And rho of R is equal to integral of distribution function. Local energy has a form U of R, this is potential, plus square root, square of velocity, other two. We note that the function f given by 9 satisfies the equation 1 in the following sense. F is a constant along the characteristics of 1. And it's easy to verify that local energy is the first integral of equation 1, Vlasov equation. Now, by virtue of lemma 2, this function, LP minus 1, is strictly decreasing on the following half interval. Therefore, P belongs to D sub R. Since P belongs to the following set, this function, composition of P and LP minus 1, is strictly increasing already. And from this equation, we have P of R is equal to composition of F and LP of R. Let us define this function f of h for h which is less or equal to E sub 0. Then equation 13 can be extended to the whole sub semi-axis. So we have equivalent equation 14, P of R is equal to composition of F and LP of R. Now, lemma 3. Lemma 3 and lemma 4 are very important because they allow us to reduce our problem to well-known Eddington's equation. First, lemma 3. Let f sub q rho u, because we define f with such index q with the help of function q, be a stationary spherically symmetric E-dependent solution of system 1,3, and let f, which we denote by f sub p, be given by 12. Let me remind you, this is 12. Because we consider fixed p, we can define LP minus 1 accordingly to p, and this formula defines f, which we denote by f sub p. Be given by 12, where p equals to rho. Then q satisfies the equation 15, the following equation. And conversely, let q satisfy 8, describes properties of q. And let f of h is given by 15. Assume that the integral equation 14 has a solution p from d sub r. This is 14. We define rho, which is equal to p, u of r, which is equal to minus lp, and f sub q, which is equal to q, depending on minus e sub 0. Then triple f sub q rho u is a stationary spherically symmetric E-dependent solution of system 1,3. Now we denote by f sub 0 the following function with shift of argument f of h plus e0. Then equation 15, if we change variables, takes the form f sub 0 of h equals to this right-hand side of equation 16. Changing the unknown function, we can rewrite equation 16 in the form 17. This is well-known Eddington's equation. Now we can give precise definition. What does it mean, extendable function? First, I would like to remind you that our aim is the following. If we have function p, we must construct triple of functions, which is a solution. But of course, this is possible not for every function p. So a function p from d sub r is said to be extendable if there exists a stationary spherically symmetric E-dependent solution f rho u or the Vlasov Poisson system 1,3 such that rho equals to p. Now lemma 4, so-called equivalence lemma. We called it equivalence lemma. Let p belong to d sub r, then p is extendable if and only if Eddington's equation 16 has a solution q with property 8 for f equal to f sub p given by 12, and f0 equals to f of h plus e0. So this is necessary and sufficient condition. This means that we can reduce our problem whether a given function p is extendable or not to investigation of Eddington's equation. Let me mention that already long ago, Eddington's equation was studied by famous Italian mathematician Tonelli, and we shall use later some of his results, which I expressed and proved in modern form. Auxiliary notations. We denote by L1 log of half interval 0t, consisting of functions p, which have contractions on closed interval 0a from L1 0A for all A from this semi-interval. And we denote by AC of 0T a set of function P such that the contraction of closed interval 0A is absolutely continuous on this closed interval for all A from this semi-interval. Now, our last auxiliary result, lemma 5. Let G belong to AC on semi-interval 0T, G of 0 equals to 0, and assume that function H sub G prime, given by the following formula, belongs to the space AC 0T. In addition, we assume that H sub 0 prime of 0 equals to 0. Then F, defined by the formula 18, is the unique solution of Eddington's equation 17. Conversely, B, if F belongs to the following space and G satisfies 17 Eddington equation, then G belongs to AC on 0T, G of 0 is equal to 0, properties I and 2I called more F has the representation 18, and G prime of X has the following form. Now we can formulate the main result of this lecture. Theorem 1. Let P belong to D sub R. Contraction on such semi-interval of P belongs to C2, so it is 2 times continuously differentiable. F be given by 12. F sub 0 equals to F of the same argument plus E sub 0. And E sub 0 equals to, as from the beginning we denoted, P capital from R. Then the following statements hold. First, Eddington's equation 16 has a unique real-valued solution, Q from the following space, which is given by the formula 19, where the function H sub F0 prime is given by the following formula 20. So as for existence and uniqueness of Eddington equation, in our case, for our problem, is okay. However, we must obtain the following. We must prove that our function, under some conditions, is extendable, function P. But this is slightly different. Maybe this is the most difficult. So P is extendable, even and only if Q of H is positive on the following interval. In other words, inequality 21 takes place. In some cases, it's easy to verify fulfillment of equality 21, but not in all cases. Therefore, we also formulated here at the part 3 of our theorem sufficient conditions of extendability. Each of the following conditions is sufficient for the extendability of P. First, F0 prime prime is strictly positive on the following interval. Now, X of R given by the following formula, let me mention that we have P from beginning, it's fixed. P capital can be calculated easily with the help of P. So this function X given by this formula is strictly positive on this interval. And C, we have 3 different sufficient conditions. If the following inequality takes place, then again P is extendable. Here, assumptions A and B are equivalent, and C implies A and B. And of course, as one can wait, proof is based on lemmas 1, 5. Now let us illustrate our theorem using examples. Let P of R be given by the following formula, and P of R is equal to 0 for R greater than R capital. Substituting P small into 5, we can calculate P capital. So P capital has the following form. The inverse function also can be calculated explicitly. It has the following form. Now we can obtain functions f as following and f sub 0 with the help of shift. Calculating derivative, we obtain f sub 0 prime. And now using previous formula for formula 20, we can calculate h sub f0 prime. Differentiating this expression, we obtain that this derivative is positive on this interval. Therefore, using second part of theorem 1, we obtain that the function p is extendable. But unfortunately, on the other hand, we can easily show that sufficient conditions of theorem 1,3b and 1,3c, 1,3b and c do not hold. So we are using this necessary and sufficient condition. In this case, it's possible. Example 2. Let P of R have the following form, and P of R is equal to 0 for R greater than R capital. Substituting P into 5, we obtain X capital. It has the following form where function f of alpha can be written as following. It's easy to see that this function f of alpha is greater than 0 on interval 0, 1. Hence, x of r is positive on this interval. Therefore, by virtue of theorem 1, item 3b, the function p is extendable. However, the sufficient condition of theorem 1, item 3c, does not hold. This
Thank you so much for your very interesting talk. Who has any question? Who has any question? Yes. I have several questions.
Yes.
Once more, thank you very much. What has happened? The is that usually one who starts with investigation of equation get a nonlinear equation, nonlinear Laplace equation. Here, as far as I realize it is equivalent to Eddington equation in your case. Yes, the question, is it so?
In this case, it's interesting. In fact, in reality, we have linear, usual Laplace operator. But the main idea, which we understood later, is connected with dimension. What's interesting that in two-dimensional case, such reduction to Eddington equation is impossible. But so only for three-dimensional case we could do it, and I mean, this doesn't mean that we before Professor Batt has studied this problem in two-dimensional case, and it doesn't mean that he couldn't do it. It's impossible. So, fortunately for us, three-dimensional case, which is more difficult. In such situation, was more convenient for investigation and allowed us this reduction. But such calculations demand maybe 3-4 pages, no more. It's more or less easy. All calculations are elementary, but they are unexpected, of course. But in two-dimensional case, everything is quite different. All calculations are made with the help of series with very complicated coefficients. It was previous paper of Jürgen Batt and some of his co-authors.
Thank you so much. Any questions to Professor Skubachevskii and perhaps to Jürgen Batt? Please, you have a question? Yes? Вы подняли руку, да?
Yes. Well, do you hear me?
Yes, we hear you.
Yes, I have two brief questions. First is, does
Yes,
the operator...
yes, we can hear you.
We hear you. Please pose your question.
Yes. Is the operator in the Eddington equation something like the fractional derivative? This is my first question. And second, what about time-dependent equations?
Sorry,
Well, first, is the operator in the Eddington equation something like the fractional derivative? Well, okay. Well, I don't hear actually. Well, okay. I unfortunately I cannot hear you. So let's discuss this later. Something.
определить, мы можем просто померить, для каких вот этих удельных плотностей, и оказывается, это не всегда. Мы можем определить вот этот самый, не в принципе вопрос разрешимости нелинейного уравнения, о том, как в явном виде определить такой U, чтобы получить сферически симметричное решение, зависящее от локальной энергии. И вот оказывается, я просто об этом не говорил в силу недостатка времени, что существуют примеры таких локальных плотностей, вот мы задаем ее, и по ней нельзя определить, но это очень сложная конструкция, и на сегодняшний момент она, почему именно в ЖВМ эта статья будет опубликована, это комбинация качественных методов дифференциальных уравнений и численных расчетов. То есть вот такая вот, так сказать, полувычислительная, так сказать, аналитическая работа, при которых это довольно хитрое. Вот здесь все эти функции P, значит, были, которые я продемонстрирую, выпуклые, либо вверх, либо вниз, ну и еще другие, которые мы считали. А здесь эта плотность, если меняет выпуклость, хотя удовлетворяет всем остальным условиям теоремы, то оказывается, вот она не является расширимой. То есть по ней вы все равно это U не определите. Поэтому, конечно, подход сведения к нелинейному уравнению, он давно известен, эллиптическому. Но здесь вопрос, повторяю, в другом. Вот мы задаем P, как по ней определить потенциал. Есть другая задача, которая тоже возникает в приложениях. Вот мы хотим определить в виде какая-то функция, зависящая от локальной энергии. Пусть эта функция задана. А как можно по ней восстановить уже все остальное, в том числе U, если Q задано? Эта задача, к сожалению, это тоже входит в нашу работу. На сегодняшний момент ее можно решить только численно, аналитически пока нет результата. Поэтому это довольно большое исследование, но оно исходит, повторяю, из физических, вернее, астрофизических постановок задач. Ну и появилось из контактов Юргена Батта с различными, в том числе и немецкими астрофизиками.
Спасибо, очень интересно. Это, да, еще вопрос появился, да? В экране.
А мы следующий не задерживаем доклад?
Вы знаете, еще у нас, мы съели перерыв, конечно,
ну, вот.
но 1 минута.
Нет, я готов отвечать, просто чтобы...
Да, интернет спрашивает.
Интернет.
Давайте, можете.
Да, так, вот я хотел спросить еще раз, вот что касается зависящего от времени уравнения, к сожалению.
Вы знаете, что зависящее от времени уравнения я тоже изучал, но это были отдельные работы, не зависящие совершенно от сегодняшнего исследования. Ну, я готов вам потом, независимо от конференции или когда вы у нас появитесь, ответить, дать ссылки. И там решались мной совершенно другие задачи. Кстати, из-за этих уравнений я с Юргеном Баттом и познакомился. Значит, это были нестационарные системы Власова, Поиссона, тоже в трехмерном случае, и для них рассматривались смешанные задачи, а эти уравнения рассматривались внешним магнитным полем, что соответствует вопросам удержания плазмы. Вот, то есть это совершенно были другие задачи, это не астрофизика, там двухкомпонентная плазма, отрицательные и положительно заряженные частицы. Ну и в отличие от других работ, в чем принципиальное отличие? То, что, как правило, рассматривали математики однокомпонентную плазму, что, в общем, не физично. И, во-вторых, они рассматривали, что будет, когда, значит, частицы достигают границы, как траектории изменятся. Но ответ физика уже ничего хорошего не будет, потому что температура плазмы 200 миллионов градусов. Ну вот это с другой точки зрения вычислительного эксперимента рассказывала частично в своем докладе Галина Геннадьевна, мы тоже с ней именно из-за этого и познакомились, за что я очень, так сказать, судьбе благодарен. Вот, и на эту тему мы сотрудничаем, пока у нас только взаимный обмен идеями, у нас нет совместных публикаций. Это очень актуальная тематика, но она совсем другая. И там уравнение Власова. Ну вот, и там, кстати, стационарные решения тоже мы исследовали. Вот сегодня об этом будет доклад Юлии Беляевой, тоже очень интересный. Но там именно плазма двухкомпонентная, но стационарное решение. Я исследовал и нестационарное решение. Ну и с Юлией Беляевой тоже мы потом исследовали нестационарное решение.
Okay, let us come to the next lecture. And the short translation of all the speech of Alexander Leonidovich is the following, that non-stationary solutions also were investigated, not only for stellar dynamics, but for plasma also. And in the lecture of Yulia Belyaeva, shortly it will be said something about non-stationary solutions. From my part, I shall add that stellar dynamics, non-stationary solution always were investigated, and it was also Jürgen Batt, by the way, who investigated, and many students of his school. So, and now this is an answer to Vladimir Nazaykinski, and now we go to the following lecturer. It is Björn Gebhard on the Rayleigh-Taylor instability. Please, Björn.
Okay, hello everyone. Do you hear me?
Yes, we hear you.
Oh, good. So yeah, thanks for the introduction, and also I'd like to thank the organizers for the invitation to this conference. So for this talk, we will shortly leave the realm of kinetic equations and go to the fluid side. It will be about the Rayleigh-Taylor instability, and I will speak about two joint works with Josef Columban, who is also postdoc in Leipzig, and Laszlo Szekelydi, who is professor in Leipzig. So the setting is the following. We suppose that at initial time we have two fluids in a container, and the two fluids have two different homogeneous densities. One density is rho plus and the other density is rho minus. And we suppose that initially they are layered on top of each other, with the heavier one being on top of the lighter fluid. And we suppose that gravity is acting on the whole system from top to bottom, as you expect. And then what you observe in experiments and simulations for this situation is that these two fluids, they begin to mix due to gravity in a more and more chaotic way. So at some fixed time, now positive, the picture roughly looks like this. So on the top part of the container, you still have a layer where you only have the heavy fluid. On the bottom part of the container, you still have a layer where you have only the light fluid, and in between you have a certain zone where these two fluids are more or less chaotically mixed. And what we are interested in, for instance, is how fast this zone opens up where the two fluids mix. So I denote these heights by A plus of t and A minus of t. And in experiments, you see that these two heights, they grow like a constant alpha plus minus times the Atwood number A times gravity times squared. So here the Atwood number is the difference of the two densities divided by the sum of the two densities. I refer to these surveys for the physics literature. And for instance, to pick a particular situation when you take cold water as the heavy fluid and hot water as the light fluid, this renders the Atwood number to be fairly small. And then this coefficient here, this alpha plus minus, just to have a number, is 0.07, for example. And in this talk, what we are interested in is a construction of such mixing solutions on a purely mathematical level. Okay, so for that, I should tell you what is the model that we use. And we take the Euler equations, the incompressible Euler equations, consisting of the three equations. The first one is the balance of momentum. So here, these two terms are the convective derivative, so the acceleration of the fluid. And we have forces given by the unknown pressure function. These are the inner forces, and an external body force coming from the gravity term. Then we have the continuity equation for the conservation of mass, and we have the incompressibility condition. So the velocity field V is divergence free. So the unknowns are here the density distribution rho, the velocity field V, and also the pressure function P. G is the gravity constant, and this En is the nth coordinate vector. On the boundary of the container, we suppose that the velocity field is tangential, and we consider these equations with given initial data. In our case, the initial velocity field is exactly 0, so the fluids are really at rest initially, and the initial density will be this interface configuration that I showed you. Most of the time I will actually speak about the Euler equations here in so-called Boussinesq approximation, which is applicable when the Atwood number is comparatively small. And then the approximation is to neglect the density fluctuations in the acceleration term on the left-hand side. Here it is kept, and here it is neglected. And this simplification from our point of view, from a mathematical point of view, introduces a symmetry between the two densities rho plus and rho minus, so we can then normalize them to be -1 and +1. So this rho that you see here, it indicates more the phase in which you are, the heavy fluid or the light fluid. And I refer to this as the Boussinesq system. Also, officially, you should say inviscid and indiffusive Boussinesq system, but we don't have diffusion terms in the equation here. Okay, so first of all, what can be said about these equations? You have local well-posedness, for instance, in Hölder classes, as written here. Then you find a local in time solution of comparable regularity. This solution is unique up to modifying the pressure function. And this was, for instance, shown by Rao, Davega, and Valli in 78 and 80. There are also local well-posedness results in Sobolev classes here by Valli, Zaytsev, or in Bezov classes by Danshin. So it's not that relevant. What I want to say is that if the initial data, ρ0, v0, is sufficiently regular, then you have a unique local in-time solution. And the point is that our initial data that we consider, our interface configuration, rho plus if xn is positive and rho minus when xn is negative, does not belong to these classes above here. And so we are therefore naturally led to consider weak solutions of the system. I recall here the definition of a weak solution for the Euler equation. It's the usual thing. You test the equation against a smooth function and you throw all the derivatives on the smooth test function. I only like to point out two specialties. So one is that the momentum balance you test not against an arbitrary field phi, but only against divergence-free test vector fields. This allows you to eliminate the pressure from the equation. It can be recovered later, but from now on we will just ignore the pressure. This is the weak formulation of divergence-free condition, and here we have the weak formulation of the continuity equation. And since the continuity equation for divergence-free vector field reduces to the transport equation, we also add by hand this condition that at almost every space-time point xt, the density only takes values from the initial values, so only rho minus or rho plus is allowed. And then we have this notion of solution with rho being an L infinity and V being only an L2 function. Okay, so when dealing with weak solutions in the Euler equations, you have to be careful what you do, because it can easily be checked that sufficiently smooth solutions conserve the total energy. So this, in our case, is the kinetic energy plus the potential energy coming from the gravity term. This is conserved, but there are examples of weak solutions where you no longer conserve the energy. It was already Lars Onsager in 1949 who conjectured for the 3D homogeneous Euler equations that weak solutions of Hölder class larger than 1/3 conserve energy, and weak solutions of Hölder class less than 1/3 don't conserve energy. And this is no longer a conjecture, so the conservative part was shown by Konstantin A. and TT in 49. And the counterexamples that violate energy conservation in 1/3 minus epsilon Hölder class were given by Phil Iset 2018, and also in this work by Bookmaster, Delalis, Sekilidi, and Vikol. And the regularity regime we look at, so we only look for L infinity solutions, definitely is the one where the creation of energy is possible. And the first thing you do in order to exclude solutions that create energy, you require them to be weakly admissible. So this means that at almost every time the total energy does not exceed the initial energy. The solutions we construct will be having monotone decreasing energy, but from the start you should require this condition, because under this condition you have the so-called weak strong uniqueness property, saying that if there exists a smooth enough solution and you take any other weak solution that satisfies this condition, then the two must be the same. So under this condition, you get this weak strong uniqueness. Okay, and from a physical point of view, it is observed that you have anomalous dissipation in turbulent flow, so the energy should decrease in some sense. Okay, what can be said about the flat interface? First of all, this interface is a weak stationary solution with here 0 is the velocity, so it's at rest. And it was already investigated by Rayleigh in 1883 and by Taylor in 1950 that this weak stationary solution is linearly unstable. There are some related nonlinear instability results. For instance, if you don't consider the interface with the jump, but the smooth density profile, or the interface problem under consideration of viscosity and surface tension. And there in these classes, for these categories, there are also some nonlinear instability results in these works. Or there are some attempts to predict the growth rate of this mixing zone that opens up based on reduction and some ansatz. But there was nothing really that said, okay, there exists turbulently mixing solutions, and this is where our theorem comes into play. I state here the version for the Boussinesq system. So in this approximation, and then this interface problem, this initial data V being 0, and initially we have the flat interface as density, this problem has infinitely many weak solutions with the following property. So first of all, if the last component in your container is greater or equal than 1/3 GAT squared, then you have only the heavy fluid, so rho is +1, and the fluid is at rest V0. If the last component in your container is less than -1/3 GAT squared, then you have only the light fluid, so rho is -1, and the fluid is at rest. And in between, so when you fix time and you take any open ball in between this zone from -1/3 GAT squared to 1/3 GAT squared, then no matter how small the ball is, you have the heavy fluid on a set of points with positive Lebesgue measure and the light fluid on a set of points with positive Lebesgue measure. This is characterized here in this inequality. So both parts are positive, no matter how small the ball is. And this property we refer to as the turbulent mixing at every time slice. Okay, so what do I want to say, remark about this theorem? So first of all, this theorem is hiding a bit the most interesting fact, which is that all these infinitely many solutions, they have a common underlying averaged profile, so to say, or averaged solution. What does this mean? So we can find among these solutions from the theorem, we can find solutions rho k vk that converge weakly to certain functions rho bar and v bar, where v bar, the average velocity, is 0, and rho bar, the average density, is given by this function. It's constant 1 above this 1/3 GAT squared, -1 below -1/3 GAT squared, and it interpolates linearly between -1 and 1 in the mixing zone. So the average density goes linearly from -1 to 1. Then I said we should pay attention to the energy, and these solutions are indeed weakly admissible. We can compute for a small time or up to an arbitrarily small error, we can compute the energy decay, which is like this. And in fact, this average profile, this linear profile, is selected after imposing certain criteria on all possible average profiles. So I don't know how much time will be left in the end, but I should say that we can construct solutions not only with this linear profile and this speed 1/3 GAT squared, we can also construct solutions with other speeds and other profiles, but this one is the unique minimizer for a certain functional which measures the maximal energy dissipation at initial times. But if time allows, I will come back to that. Let me here continue with the remarks. So also I should say that this form of the averaged profile, this rho, is correct as long as the mixing zone, this turbulent zone, does not hit the bottom or the top of the container. When this happens, we by hand show that the solution can be continued past this until it demixes and reaches the stable configuration, where then the heavier fluid is below the lighter fluid. So in that sense, we construct heteroclinic solutions from the unstable interface configuration to the stable interface configuration. But I should say that, unlike before, that this is a construction by hand, not based on any selection criteria. Also, I should say that this theorem I showed you for the Boussinesq approximation was our second attempt. Before we had, together with Laszlo Székely, attacked the full Euler equations, and we could construct similar solutions, but only under this condition that the quotient of the two densities is sufficiently large, which renders the Atwood number in a quite high range, larger than 0.845. And so we asked ourselves, okay, what happens for low Atwood number? And this led us to looking once more at the equations in Boussinesq approximation. By now, I think if we make the modifications that we did in the Boussinesq case, also here, that we can also get rid of this condition in the full Euler case. But the first one was the one with Laszlo Székely. Okay, let me sketch the proof a bit. So the proof relies on the method of convex integration, which was introduced by Camillo De Lelis and Laszlo Székely in 2009 to the context of fluid dynamics. And this method served as an engine for counterexamples. For instance, also the ones that I mentioned earlier by ESET and so on, they rely on this method. And later it was also used to describe turbulent behavior in actual situations. So here are some examples. This is not for the Euler equations, but a slightly simpler equation, the incompressible porous medium equation. There the history is a bit longer than for Euler. And here these are two works for the homogeneous Euler equations, where you have turbulent solutions emanating from vortex sheets. And in these lines of works, also our result has to be seen. I should also mention this, that there was a convex integrations result for the Boussinesq system, but with smooth initial density ρ0. So it could not be used to model the horizontal interface configuration. Okay, to sketch a bit the proof, I have written here again the Boussinesq system. The only difference to before is that I split the matrix V tensor V into its trace-free part here and its trace, which I pull together here with the pressure. And then what you do is you introduce for every nonlinear quantity that you see in your equation, you introduce a new linear variable. So this V tensor V traceless is replaced by a matrix sigma, and the product rho V is replaced by M for momentum. And then you consider on one hand this linear system here, but of course you don't have to, you should keep in mind what you replaced. So we also have these pointwise conditions now, that the sigma should be V tensor V traceless and M should be rho V. So we have the linear equation, these pointwise constraints, and we also add another pointwise constraint allowing us to prescribe the kinetic energy density. So we have 1/2 V squared to be a certain continuous function E0, and the product of rho times a certain other continuous function E1. And we are the ones that later will give these functions E0 and E1. But for now, let us consider this as given continuous functions. And then all these pointwise constraints, so this 1, 2, 3, and this one that we introduced, they form a family of sets in some Rn, capital N, of certain dimension. And this is then the reformulation of the Boussinesq system as differential inclusion. So the functions rho V M sigma should satisfy this linear system star, and it should take values in the set K for almost every xt. So this is the equivalent reformulation for L infinity solutions, for instance. And then what you observe is, what you observe is that if you have a sequence of such functions that solve this linear system star, and they take values in k, and you consider a weak limit of such sequences, then the weak limit still satisfies the linear system because we deal with weak solutions. But the pointwise condition is now replaced by, instead of k, we end up in the convex hull of k. And roughly speaking, the reverse statement is convex integration. So if you take a set bar that is continuous, solves the linear system, and takes values in the strict interior of the convex hull of K, then you find infinitely many weak solutions near this set bar, and near means with respect to the weak L2 topology. So this means in order to construct solutions, you need to investigate the linear system under the condition that you take values in the interior of the convex hull. And for that, it's key, and this is one of the most non-trivial aspects of this, to know the convex hull K. So to the set of conditions I have shown you before, the relaxation, so the convex hull explicitly can be computed and consists of these four conditions. I will not go into detail. I think this lambda max means the maximal eigenvalue of this matrix should be less than this number that you see here. I just want to stress that this is important. It is important to have this relaxation. And then these inequalities together with the linear system form the subsolution system. So these are the averaged motions, so to say. And then you see that we have quite some freedom of choice in picking these functions E0, E1. Also, we have inequalities, so a lot of choice here instead of equalities from before. So there's a lot of freedom in constructing the averaged solutions. So this, on one hand, it's good because this allows you to, in some situations, first of all, get a solution because it's easier to find sub-solutions. But it also gives a problem that you can construct a lot of average solutions. And so a certain selection or investigation of extremal sub-solutions is necessary. And this investigation of sub-solutions can also give you information about solutions to the Euler equations that are not obtained by convex integration. Because if you take a solution of Euler and you average, you end up also in the convex hull. So you get also sub-solutions from averaging and from considering weak limits, as I illustrated before. I think then my time is over, am I right? So we then impose, to construct this 1/3 GAT squared, we impose maximal in energy dissipation initially and find this this identity profile and the 1/3 GAT squared as a unique minimizer. Okay, then here, if you're interested, here are the works. Then yeah, thank you for your attention.
Thank you so much, Bjorn. Now we have some time for questions. Please, Alexander Leonidovich.
Bjorn, first of all, I'm very glad to hear you. Tell me, please, do you have at this moment some analogous of video which you have demonstrated us several years ago at our seminar?
You
of
mean
mixing the
this?
fluid.
I don't know if I have it available here. I know what you mean. This was a numerical simulation which was not
Yes,
done by
yes,
me.
yes, because it gives, it's very impressive.
Sorry, I don't think I find it in time.
Okay, maybe later, if it is possible, you will send us in order to put it at the site of our conference jointly with your lecture, if it is possible.
Yeah, okay. Moscow.
Thank you.
Okay, thank you very much. Any questions to Bjorn? Bjorn, I'm also great to hear from you.
Yeah, likewise.
Yes. So, question. My question is the following: what you consider two types of equations? One you call earlier equation and another Boussinesq equation. Show us the difference between them.
The difference?
Boussinesq equation and earlier equation.
Yeah, okay.
You have different results in different papers even on this subject.
So the difference, so for the Euler equation,
And Boussinesq, it seems to me that you have even on some slide, both of them.
So here's the Euler equations.
I see, yes.
And the difference is this row here and here. So in the Boussinesq, which is on this slide, there's no density dependence in the convective derivative, in the acceleration term.
And there is a difference of solution. Yeah. What is easier? Which equation is easier?
This is now Boussinesq.
This is Boussinesq.
Which one is easier, you ask?
Yes.
So for our method, I would say there's not so much difference in the main point, which is the getting this relaxation, these inequalities that I showed you, this convex hull. So this is a comparable difficult task. If you know one, it helps you how to find the relaxation for the other. And then what is the advantage of Boussinesq is that there is a certain symmetry introduced because you have normalized the rho to be -1 and 1. And this allows you, allowed us to solve the variational problem that we set up in an explicit way. And before, for the Euler without Boussinesq, we followed a different strategy for finding subsolutions, for finding the averaged motion.
Thank you so much. Any question? Yes, please, Pavel Igorevich.
About convex integration. There is other way to construct a solution, more or less classic, for example, viscosity limit from Navier-Stokes or capillary limit by the surfaces. In principle, there is two different other approaches. The question is, can we guarantee or have you some arguments that, for example, viscosity limit from Navier-Stokes also covered by your theory, or maybe it is separate?
No. So if you consider viscosity limits from Navier-Stokes, then what you get, the weak limit that you get, should be a subsolution. So I cannot give you a rigorous result for the inhomogeneous Euler, but it should be. I can look it up for the homogeneous Euler case. So if you take Rayleigh-Hopf solution for Navier-Stokes, and then you consider the limit viscosity to 0, the weak limit that you get is such a subsolution to Euler, such a averaged solution.
Yeah, but the question, maybe the theory of inhomogeneous Navier-Stokes equations for with non-constant density is also exists. You can find it in Leon's book. But the question is about maybe the number of convex integration, maybe give some other solutions or something like this.
Okay.
There's no physical meaning. This is the question.
Sure. One has to be careful. So here, it could be a priori that, and this you can do, that you can construct more solutions with convex integration than you obtain as zero viscosity limits. For instance, with convex integration, you can construct solutions that increase energy, which you can never realize as zero viscosity limit from Leray-Hopf solutions. So there are definitely unphysical solutions constructed by convex integration. So you have to be careful.
Thank you.
Any other questions? So if there is no question, then we have 1 or 2 minutes for our interval before the next lecture.
Knopf, are you here?
Yeah, hello. Can you hear me?
Yeah, we can hear you well.
We have the next lecture. The topics of the lecture and the lectures are so interesting. that we have no time for intervals between lectures. But now, nevertheless, shall the following lecture, Knopf and Weber.
Yeah, can you see my slides?
Regensburg, Germany, and Lund University in Sweden. The 2 and 1/2 dimensional Vlasov Poisson system, well-posedness and stability of confined steady states.
Okay, so thank you for the kind introduction, and of course, thank you to the organizers for inviting me. It would, of course, have been nice if I could have been in Moscow myself, but at least it's great that I can give this talk in this online format. Yeah, as it was already said, the topic of my talk is the 2 and 1/2 dimensional Vlasov Poisson system. And in particular, I want to talk about the well-posedness and the stability of confined steady states. And as it was said, this is actually a project that was done in a collaboration with Jörg Weber, who is currently at the Lund University in Sweden. So basically, the situation that we are considering is we want to describe a plasma, which is, of course, a large ensemble of electrically charged particles. And in this situation, we just consider 2 types of particles, which are cations, so positively charged ions, and electrons. And as we basically just want to study this model from a mathematical point of view, we just set all physical constants, like, for example, the mass and the charge of the particles to 1. And in these kind of Vlasov type models, as we've already seen in the first talk of this section, it's basically the idea is to not consider all the particles separately, but in a more statistical way by considering their associated distribution functions. So here we have this distribution function F minus which describes the electrons, and F plus, which describes the cations. They are both non-negative functions. And they basically tell us how many particles with velocity p are located at the space point x at time t. And I mean, as these particles are charged, they interact with each other. So particles with different charge will attract each other, and particles with the same charge will repel each other. And this is basically incorporated in the model by the self-consistent electric potential, which is induced by the particles, and the associated field. So this U here is the electrostatic potential. It depends on time and space. And then minus the gradient of U is then the associated electric field. And here I should maybe mention that we just consider electrostatic effects, so no electrodynamic effects like we would have in Maxwell's equations or in the Vlasov-Maxwell system. So here we just basically neglect these effects and just consider the electrostatic interaction. Yeah, and now later we also want to study steady states of this model, so of this kind of plasma. And unlike in the first talk of this section, where it was the Vlasov Poisson system in the gravitational case, in the plasma physical case, where the interaction is basically in the other way, so there's no attraction between equally charged particles, but they repel each other. It's basically a different sign, and here we actually need some kind of exterior field to actually allow for steady states. And in this model, we will add an external magnetic field, which is associated with an external magnetic vector potential. So this function A here, depending on time and space, is the external magnetic vector potential. And then B is given as the curl of A. This is the external magnetic field. And this description basically has the advantage that the physical condition that the divergence of the magnetic field is always 0 is already incorporated here, because the divergence of a curl is always 0. So that's why this description with a vector potential is quite convenient here. Yeah, and basically, if we look at the dynamics on the Lagrangian levels, then we can say that the particles obey Newton's law of motion, which basically means that the time derivative of the spatial coordinate of a particle is the velocity, and the time derivative of the velocity coordinate is the acceleration. And since the mass of the particles is set to 1, this is basically just the force. And the electric field here interacts with the particles directly, whereas the magnetic field interacts with the particles via the Lorentz force. So here we actually have the cross product with the velocity vector. And basically on an Eulerian level or a macroscopic level, the time evolution of these distribution functions, which are associated to the plasma, is determined by this Vlasov-Poisson system here. So the first line, which are actually two equations, one for minus and one for plus, for both sorts of particles. This is basically the Vlasov equation. So that's a transport equation which describes the time evolution of these distribution functions. And here we have this self-consistent electric field, which solves a certain Poisson equation, and therefore it can be described as the Coulomb potential of this quantity rho f. And the rho is actually the charge density. So this is the integral of the distribution functions with respect to the velocity. And as I said on the first slide, the external magnetic field is just given as the curl of this external vector potential. And we also have some kind of initial condition to basically complete the model. And this Vlasov-Poisson system, especially in the case where the external magnetic field is 0, which is, so to say, the standard case, has really been investigated extensively already in the literature. So I just wanted to sum up the most important results on its well-posedness. So in 1952, the local classical well-posedness was studied by Kurt. So it's basically the existence and uniqueness of a local and time classical solution. And then in 1977, a continuation criterion for such local classical solutions was established by Jürgen Batt. And it basically states that a local classical solution can be extended in time as long as this quantity P here remains bounded. And this P, what this actually describes is something like the maximal radius of the support of the distribution function with respect to the velocity coordinate. So if this is under control, the local solution can be extended. And this could then eventually be used to prove the global classical well-posedness of the Vlasov-Poisson system. And these were really seminal proofs which appeared almost simultaneously, at least the preprints. So one was by Lyons and Pertam, and the other one was by Klaus Pfaffelmoser. And yeah, as I said, they were really almost simultaneous, but they were both different, so both proofs really somehow have their merit. And now in the case where the external magnetic field is actually non-trivial, the global classical well-posedness of this model was actually proved by myself in 2018. And basically, I mean, the local existence of solution is not much different than in the case without the external field, at least if it's sufficiently regular. And to extend the solution to a global and time classical solution, I basically adapted this proof by Klaus Pfaffelmoser. And the crucial idea was that an external magnetic field does not change the modulus of a particle's velocity, but only the direction. And by this velocity support could also be bounded in a similar way. And also in this paper and in a follow-up paper with Jörg Weber, we studied the optimal control theory of this model, where we took this external magnetic field basically to be the control in these kind of optimization problems. Yeah, but now in this talk, I don't want to talk about this full three-dimensional model, but we consider kind of a reduced situation, as you can see in this picture, where we consider the plasma in some kind of cylinder, which is for mathematical reasons assumed to be of infinite length. So inside the cylinder, we have the plasma, and maybe on the boundary of this cylinder, we can have some magnetic field coils, which then induce this kind of external magnetic field that we have in our model. And as a simplifying assumption, we assume here that the distribution functions of the plasma basically look the same in every cross-section of this cylinder, which leads to the fact that the distribution functions are actually independent of this x3 component, which points in the direction of the cylinder axis. And then we only have basically two spatial components left, but still three velocity components, because we still allow for velocities in the direction of the cylinder axis. And this is where the name 2 1/2 dimensional comes from, because two space dimensions, three velocity dimensions, if you take the average, then you basically have 2 1/2. Yeah, and the 2 1/2 dimensional Vlasov-Poisson system then looks almost exactly like the full 3-dimensional one. But there's one difference in this electrostatic potential here. The description changes. So the Coulomb potential in 2 dimensions has a different kernel, and this kernel here is given by this kind of logarithm here. And even though we have now reduced the dimension, the global classical well-posedness of this model is still not clear. I mean, a lot of things get much easier than in 3 dimensions. So basically, the main problems that Lyons, Pertam, and Pfaffelmoser had in their proofs do not appear here. But we still face some different problems because of this logarithmic kernel here, which is not non-negative, unlike in 3 dimensions. And it also does not vanish at infinity. So, for example, things like integration by parts gets a lot more difficult for terms depending on this electrostatic potential. So basically what we had to do is we had to prove global classical well-posedness for this model on our own. And if we have sufficiently regular initial data, so the initial data are supposed to be C1 functions with compact support in R5. So the 5 is for 2 spatial and 3 velocity components. And we assume that the external magnetic vector potential is sufficiently regular. And under these conditions, we could actually also show that there exists a unique global and time classical solution of this 2 1/2 dimensional Vlasov-Poisson system. And basically a key ingredient in all these kind of well-posedness proofs, at least for the global existence, is always the energy conservation. So here we have this energy here, which is denoted by H, because it basically stands for Hamiltonian, as we have some kind of Hamiltonian dynamics. This is given as the sum of the kinetic and the potential energy. And this is constant in time, which is a typical property in general of hyperbolic equations. And so in the 2 1/2 dimensional model, the kinetic energy is basically the 1/2 times the modulus of the velocity squared times the distribution function and then integrated. So this quantity is always non-negative. But the potential energy we have to write basically as the integral of the product of the electrostatic potential and the charge density. And unlike in 3 dimensions, it's not possible to show that this is non-negative, and this is due to this logarithmic kernel in the convolution describing this electric potential. And what's always important in these, if you want to show that a classical solution exists globally in time, you always need some kind of bound on the kinetic energy. And of course, if the total, you can express the kinetic energy as the total energy minus the potential energy, and the total energy is conserved. And if the potential energy is non-negative, as in 3 dimensions, this is of course trivial that the kinetic energy is then bounded. But in the 2 1/2 dimensional case, we have minus the potential energy, which looks like this. And since this does not have a sign, basically additional estimates are necessary to handle this kind of term and to show that it's at least bounded in some suitable sense. Yeah, but this could still be done, and we could prove the global classical well-posedness also in the 2 1/2 dimensional case. Yeah, but Yeah, I mean, in this kind of applications which are behind these models, I think the most important one is basically thermonuclear fusion, where you have some kind of fusion reactor in which the plasma needs to be confined in some certain reactor. As you can, for example, see in this picture, I mean, here the plasma really has some certain distance to the wall of the reactor, which is really desired, and the crucial problem in this in the fusion research, because if the plasma actually would touch the wall of the reactor, it would of course cool down, which makes the fusion process impossible, and also it maybe would just damage your reactor. So one of the crucial problems is really to ensure by the magnetic field that the plasma remains confined somehow in the fusion reactor. And for time-dependent solutions of the Vlasov-Poisson system, this is really a very challenging problem, which I think is not really solved, at least not if the magnetic field is not singular in some sense. But at least we could show this for time-independent solutions, which are so-called steady states. So what we wanted to investigate was the existence and also the stability of such steady states, which remain somehow confined in the interior of the cylinder. Yeah, and as I said, I mean, steady states are just time-independent solutions of the Vlasov-Poisson system. So all these quantities like F0, U0, and the external quantities A0 and B0 are now independent of time and solve the Vlasov-Poisson system in a stationary sense. And then we say that such a steady state is confined in a cylinder with radius r, which will be just a given radius. If the distribution functions of the plasma are zero, if the norm of the spatial variable is larger than r. And basically what this says is just that outside of the cylinder with radius r, there are no particles, which means confinement. And then it's, of course, only interesting if we talk about non-trivial steady states, because I mean the zero solution is always a steady state, but a very boring one. And we just say that a steady state is non-trivial if both of these distribution functions, so both for plus and for minus, are not identically zero. Yeah, and in the following, because there are already a lot of results on steady states in the literature, I just wanted to mention at least some of them. So one of the first ones, I think, was the existence of steady states in bounded domains, which was proved by my PhD supervisor Gerhard Rayleigh in 1992. And then in 1999, the nonlinear stability of steady states, now not in bounded domains, but on the whole space under some kind of external electric field, were investigated by Batt, Rayleigh, and Vukatinovich in 1999. And then in 2014, the existence of confined steady states under an external magnetic field now was established by Alexander Skubachevskii. And this was done in the case of where the self-consistent electric potential U vanishes. So, and this is actually not a strange assumption, because if the particles, the ions and the electrons are completely mixed, then there's no charge separation, and then this electric potential will be zero. And so this it's natural that you want that this property is conserved over time, basically. Then there was a paper on confined steady states, also under an external magnetic field, where the confinement was done in half space by Belyaeva in 2017. And then in 2019, there was a paper by myself where I showed basically I generalized this existence of steady states result by Skubachevskii. So also with an external magnetic field, but now the electric potential induced by the particles is now allowed to be non-trivial. So in this case, this is also possible. And then I also want to mention a very recent paper by Belyaeva, Gebhard, and Skubachevskii, where they present a very general approach to construct confined steady states in different scenarios and also under the influence of an external magnetic field. So, and now I briefly wanted to give you the idea how the construction of steady states worked in our case. So we just assume that we have some external magnetic vector potential, which is sufficiently regular, so it's a C2 function. And in the following, because we consider this cylindrical situation in an infinitely long cylinder, we use cylindrical coordinates. So the radius, the angular, and the c is basically the variable which points in the direction of the cylinder, and the corresponding unit vectors. And then, similar to the first talk, we need some quantities which are already solutions of the Vlasov equation, or let's say they are invariants of the characteristic flow. And if we assume that the electric potential is already given and actually symmetric, so symmetric about the cylinder axis, so it depends only on the radius, then this quantity E, which is somehow the microscopic energy of a single particle, this quantity F, which is basically the angular momentum of a particle, and this quantity G, which is the momentum of a particle in the direction of the cylinder axis. These are basically all already solutions just of the Vlasov equation if the electric field is basically the one that comes from the given electric potential. Now the ansatz is, because I mean these kind of solutions are, of course, cannot be confined or anything. So the idea is to really obtain a steady state, that we use suitable C1 functions and make this ansatz that the F0 basically is this function theta, where we plug in the particle energy, and the function psi, where we plug in these other invariants. And now we want to show that by this ansatz, we actually get a steady state. Because, of course, what remains to show is that we can adjust this potential U0 in such a way that it's actually the correct potential that is induced by this kind of function F0. And the idea here is if we make this ansatz, then the corresponding charge density can be interpreted as a functional of this potential U0, because this particle energy depends on U0. And yeah, and because this electric potential was assumed to be actually symmetric, we can basically reformulate its description in cylindrical coordinates, and then we get this kind of formula here, which depends on this charge density rho. And since this is a functional of U0, we basically have some kind of fixed point problem for this potential U0. And this can be solved in different ways, either by a direct fixed point argument, or, for example, by applying Schäfer's fixed point theorem. And if this can be solved, we basically obtain the existence of such a electric potential U0, which then actually, by this construction, corresponds to this function F0. So the F0 and the U0 then solve the stationary Vlasov Poisson system together, and that's why it can then actually be considered a steady state. And the important property is that if we basically prescribe any given radius r, then we can find suitable assumptions on this function theta and psi, which appear in this ansatz for the steady state, and assumptions on the external vector potential, which basically means that it needs to be sufficiently strong. And under these assumptions, it's actually possible to show that the steady state F0 is, first of all, non-trivial, has finite total charge, and most importantly, it's confined in the cylinder with this given radius r here. Yeah. And okay, so that was basically about the existence of these kind of steady states. And now we also wanted to investigate their stability, at least with respect to perturbations. Basically, I mean, the idea is if you start with a solution that is somehow close to the steady state, you want to show that the time-dependent solution at least remains close to the steady state over the course of time. So we now start with basically a non-trivial confined steady state, so such a one which we constructed on the slide before, of course with suitable assumptions on these functions and the vector potential. And then the perturbation is basically a compactly supported function, which also needs to be actually symmetric. So we can only consider these types of perturbations. So actually symmetric with respect to the cylinder axis. And we also need the assumption that it has the same total charge as the steady state. And if we now take this perturbation function as the initial datum, then since we have global classical well-posedness, we can associate such a function f, which is the global classical solution, to this initial datum. And for this, we actually could derive some kind of stability estimate, which at least roughly looks like this. I didn't want to write it down in full detail. It's already technical enough. But what it basically says is that the difference of the solution which starts in the perturbed initial datum, so to say, the difference with the steady state in the L2 norm remains bounded. And on this right-hand side, we basically all quantities become small if the perturbed initial datum remains close to the steady state. And I mean, here it's also important that these functions here, C, capital C and small c, which we know explicitly, but they are very, very technical expressions. They do not depend on time. So this means actually that we have really some kind of stability result in the sense of a dynamical system. And I actually don't know how much time is left, but yeah, I think this was actually, yeah.
1 minute.
1 minute, yeah, then maybe I should just say, of course, I mean, we now have the stability result, but this, of course, still does not mean that we actually can control the support of this perturbed solution. I mean, this would, of course, be very nice if we could also show that the time-dependent solution that starts in the environment of such a steady state remains also confined. But this we could not show yet because, I mean, the stability in the L2 norm does not really guarantee this behavior. But nevertheless, I mean, it's at least some kind of stability result that we have for such confined steady states. So, and yeah, this was basically what I wanted to talk about today. So thank you for your attention.
Thank you so much. It was very interesting lecture for us. And I think Julie Belyaeva, Skubachevskii, and me have many questions to you. Please, who has a question? Any question? Yes.
I have the following question. Yes, okay. Concerning first, do you consider only auxiliary symmetric perturbations or arbitrary perturbations of stationary solution?
No, so far we can only consider actually symmetric perturbations. That's
yes, I understand. Second, tell me please, are you living at some finite interval, for example, 0 t capital, or at infinite half interval, like 0 infinity?
What do you mean?
Which interval for stability of solution?
I mean,
studying?
The stability estimate that I presented here is actually really on an infinite time interval. But of course, infinite. I mean, it's only in the L2 norm. Yeah.
I see. Thank you.
Yeah. I mean, it would of course be nicer if it could be a stronger norm, or if there would also be some kind of stability result for the support of these kind of solutions. But so far this was not possible to show.
Yes, but the most important thing, investigation of support, because it mustn't reach the boundary. This was the main idea of all my papers devoted to, how to say, to plasma.
Mm. Yeah, maybe this is, it could be possible, of course. I mean,
Because the
in finite
estimation
time,
of
but
supports is very important.
yeah, of course. This is the most important property, but at least for a result on an infinite time interval, we didn't see any chance to show it so far.
Okay, thank you. Okay, who else asked to? Who else wish to ask? Bjorn, please. Tell us, please. What would you like to ask?
Hi. So I wanted to ask you. Usually you can construct quite a lot of stationary solutions, right, with this cutoff function method. Is there one choice that is particularly stable, or which one of these are stable? Or you have a family of...
It's a bit difficult. So it's not, I mean, in the astrophysical sense, you really have some kind of explicit functions which lead to steady states. I mean, here we basically have just these C1 functions where we plug in these invariants, and on these, so this theta and psi on the slides. And on these, we just have a lot of conditions, of course, like, as you said, with this kind of cutoff energy, this is always a condition that you need. But I wouldn't say that we really saw like a special family of steady states, which are really, viable.
Very stable or something. I don't know. Okay.
Not so far. I would like also
Thank you.
To ask you the following. You consider your potential in the whole space, but did you consider mixed problems? Because in reality, for thermonuclear reactor, you have either, in the case of mirror trap, you have cylinder. This is not the whole space, even in cross section. In the case of tokamak, also you have torus, but not the whole space. In this case, you cannot write your potential U in the form of Newtonian potential, because in general case, you cannot write green function in explicit way.
Yes.
Did you study mixed problem? I mean, some domain, and you have some boundary conditions for potential U and Poisson equation in this domain.
Yeah, I mean, so far we did not study any boundary conditions. I mean, it depends a bit on the modeling, I would say. I mean, if you basically just consider the particles interaction, then usually I would say that they do not really see what happens at the boundary, at least on the level of the electric potential. I mean, I know that there are some kind of models with boundary conditions like this perfect conductor boundary conditions or these things, but we did not have a look at this. I mean, it would of course probably also be possible to apply similar techniques there, but at least we just considered the electric potential on the whole space.
Thank you.
Thank you so much. Any more questions? So I have a question, much even more interesting perhaps for me. Best regards to your supervisor, Gerhard Rayleigh. Best regards to him. We met with him before this paper, 1992, published. And I, in Germany, in Lambrecht, due to invitation of Jürgen Batt. And we met with Gerhard Rayleigh. And what do you think? What did I say said that time to Gerhard Rayleigh? when he said, "Oh, you know about Vlasov equation much more than I." What do you think? I shall answer this question to you. This question is the following: what is your function that your this f0? What are function? What are this function? Show us this function, and we shall discuss about the property of this function. Show us this function.
Yeah,
you see what function? What is dependent upon energy of this your theta of energy? You see, you take a product of a function of energy, yes?
Mm.
Yes? And the product of the other two components, two conservational laws, yes? I would like to stress that you can take any function of 3 variables and that the result will be the same.
Yeah, that's true. I mean, for the existence of steady states, we could really just take one function which depends on all 3 variables. But for the stability, we really needed this kind of splitting.
For stability result, Jürgen Batt informed me. Jürgen Batt is here, yes? He will perhaps justify what he said to me. Jürgen Batt informed me that even for in this situation, you need only monotonicity of energy, and then you will get stability result. Monotonicity of energy. And Jürgen Batt stressed to me that if it is not monotonic, then there is no stability. Of course, we discussed only this paper of Gebhard Rayleigh when there was function only of energy. 1992 Gebhard Rayleigh paper, which was not yet published. Yes.
Mm-hmm.
And Gebhard Rayleigh that time used monotonicity for proving of existence of and the uniqueness of them. And I said to him that one needed this monotonicity, and there is some inequality that I showed to Gebhard Rayleigh that allows us to prove existence and uniqueness. This is a property of nonlinear elliptic equation. That is the problem that I think you also have. Have you monotonic? Do you suppose monotonicity of energy in this situation?
Yeah, we need some kind of monotonicity assumption on this function where we plug in, let's say, this microscopic energy. This we need in any case. The point is, you could of course also construct steady states which only depend on this energy, but for the confinement you actually also need this kind of other variables like the angular momentum and the momentum in the cylinder direction.
Mm-hmm. For this, we investigated also with my student Arkhipov and even with Axel Klar from Kaiserslautern University, it seems to me. Oh no, this is paper without Klar. Stability result is published already. Also for this situation of only one function on energy. Yes, this is also in was also in 90s. Yes, in 90s. So this is my best regards to Gebhard Rayleigh. How is he?
So what was the question?
My question is, how is Gebhard Rayleigh?
Yeah.
Well, okay. So now we have time to another the next lecture. Who is the president of this? Mikhail Valerianovich, is he here? Mikhail Valerianovich is not here, so I shall continue the next lecture is lecture of Yulia Belyaeva, Yulia Olegovna Belyaeva, Björn Gebhard, and Alexander Leonidovich Skubachevskii. It is, yes, it is called on some examples of stationary solutions to the Vlasov Poisson equation.
Probably. And today I'm going to tell you about stationary actually chapter or something. Oh, sorry, where's my presentation?
20 minutes.
Okay. So here you can see the problem. We consider the Vlasov Poisson equation in the following term. So here I have beta, where beta is +1 and minus. This unknown function, and this is the distribution functions of positively charged ions or of electrons. And also phi is a function which depends on x and t, and phi means the potential of self-consistent electricity. Also, we have second equation, this equation. Basically, it's two equations for each beta, and here m beta are ion and electron. C is the speed of light. C, which depends on x, is the induction of magnetic field induction. Sorry. So it's clear the gradients with respect to B and X. And here functions F beta depends on X, V, and T. So we have the distribution function at the point X with velocity V at the time T. Usually we consider this problem with initial conditions in a physics. Boundary condition form 4. So depending on the so if we are talking about it, consider the kinetics of high temperature plasma in a device which is tokamak. So here we have a brief scheme. Here we have plasma and thematically the magnetic line, the mirror trap. Then we have a domain, a cylindrical domain. So also here we have brief scheme. Here is plasma and magnetic line. Here and here as well. So the main question that we have here is the existence of stationary solutions to this problem. At the moment, by stationary we mean time-independent solutions, and later we will give some strict definition of it. And of course, we are interested in plasma confinement solutions, which means that we have to consider at least this type of properties that support of the distribution function should be not intersect the boundary of the domain, but ideally it might be compact. And also we consider a two-component plasma model, which is really important because plasma is quasi-neutral matter. And here we have some citation. So if we are talking about Vlasov equations, we of course have to emphasize the influence of scientific school of Professor Batt. Here we have one of his paper, and of course we have to emphasize the work of Professor here today. By Professor Skubachevskii and me, it was constructed some types of stationary solutions, but with a trivial potential. And today I'm going to show you some examples with non-trivial potential. So here, and recently it was published papers by Professor Knopf and Professor Rayleigh. And also it is considered, as you might heard before, the stationary solution to the Vlasov Poisson. And the result that I want to present today is from our joint work with Gebhard and Alexander Skubachevskii. And I'm going to present solutions in a cylindrical domain. So basically, the approach to the proof of the results, which we are going to say today, is based on 3 points. Of course, it is method of characteristics to the Vlasov equations, conservation law, and method of sub and super solutions to nonlinear, let's say, elliptic problem. Okay, so here we have strict definition of stationary solutions. So the triplet of functions in this form, where all of these functions are time independent and of the following classes, such that the following property is fulfilled. So we're going to say that this triple is a stationary solution to the equations 1, 2, and the boundary value condition 4. Of course, third condition now disappear. Okay, so first let's consider the case of an infinite cylinder. So here we have our infinite cylinder, where Q is the following two-dimensional disk of the following radius, and we assume that our magnetic field is directed along the x3 axis here of the following. And Professor Knopf already mentioned his result, and here we used this type of restriction. So our goal to construct the stationary solution first in a cross section. And here we have the following substitution. So we assume that our F beta now has the following form, as well as potential now depends on x1 and x2. So psi beta now functions with the following properties, yes? And using this substitution, we will restrict our problem to the now two-dimensional form. And okay, let's have the problem 5. For this, construct some first integrals, and the energy of the form, as mentioned here, would be the first integral to the corresponding characteristic systems. And also, if we assume that now our function phi depends only on this type, then the following function will be also a first integral. So now we have two first integrals for the restricted system. And the following proposition we will have. So this result is for the restricted system. So let psi beta will be the differentiable function. Basically, it's a cutoff function with respect to cutoff parameters E0, 0, and I0, as well as parameter B here. So there exists a stationary solution of the following form, yeah, where we will have our potential with the following structure. And what should we also highlight? That support of our solutions will consist in the following domain, where S0 and R0, we can even calculate them, and it has the following structure. But what it means? It means that we constructed solutions which supports we can control by two different ways. One way is mathematical, so we can pick the parameters, so the cutoff parameter here, and we can mathematically control their support. But also we have here this formula where B, I would like to remind you, magnetic, the component on the magnetic field, and the bigger our magnetic field, yeah, the stronger it will be. Well, so it has this type of influence to the support, our spatial support. And after this, we can go back to the three-dimensional case, and in such a way, we will have already a stationary solution for three-dimensional system with the following structure. So our density distribution functions will have the following structure, and phi will be on this form. And in such a way, we obtain stationary solutions whose spatial supports are contained in arbitrary small cylinders, which we can control by, for example, the changes of our magnetic field, or by choosing the cutoff parameters. So that was the result for the infinite cylinder, and now we consider a bit different magnetic field with the following form. So here we have now P, which depends on X, given by this formula, and basically if we put A as a constant, we will have the same magnetic field as before, and A here is a differentiable function, and for this type of system we will have also the following first integrals. Okay, and similarly to the previous case, we can construct the stationary solution, which depends on phi, and have the following structure, where also E and E0 beta and I0 beta are the cutoff parameters. Okay, probably here I will stop. I hope you have some interesting questions. I would be happy to answer some.
Thank you so much, Yulia Olegovna. Any question to Yulia Olegovna? Then I have Innocenty, please.
In this form, but how can you ensure that divergence of it is zero? Divergence of the magnetic field must be zero.
Yes, of course. It should be.
How you check it?
How we check it? Yes, it's a good question, and it's not easy to me to give you a quick example, quick answer, but like I can show you where we check it, and of course it should be the divergence. Okay, yes, sure. Here should be plus for sure. Yes. Thank you. Mm-hmm.
Yes, there is a simple answer. So, are you satisfied, Innocenty? Okay. Yulia, perhaps somebody else has any question? Pavel Igorovich.
Is it possible to construct singular solutions? I mean the following. Давайте по-русски скажу, что тут. Формирование струй джетов у молодых звезд. Такой распространенный феномен. У вас есть функция распределения, есть скорость, есть плотность. Казалось бы, полный набор переменных для описания этого явления. Но там должна быть сингулярность на оси. Вот можно такие решения строить?
I shall translate the question. The question is very interesting, so I shall translate it. For formatting of jets in young stars, we have to have single solutions in zero. Is it possible to construct such single solutions?
Okay, so let me think. So you mean that in this case we will have already like a distribution function is given, right? So we will have like, or not? Maybe
there is something fantastic that the f should be f prime. It is measured. Mm-hmm. Yes, it should be have some component at infinity, something like this. Then b, it is something localized fantastic, but на оси симметрии вращаясь.
Alexander Leonidovich Skubachevskii asks, where do you have to have singularity?
Они увязаны, без магнитного поля по нынешним представлениям нет струй. Но речь идет о крайне простом. Вдоль оси симметрии имеется решение, скажем, с бесконечной скоростью. Плотность, скорее всего, там не имеет.
On the axis of symmetry, there is particles with infinite
speed and finite energy.
How that,
то есть решение которых скорость.
I don't know any particle which have
like
infinite speed and finite energy. It is
yes, at the axis you density, the size of the jet is it is one-dimensional formation. Therefore, the mass may be zero, but the energy is finite. V contains to infinity, and but rho is some integrable function. It is singularity. It is strong singularity.
Very interesting question, and here, like what I can say from my still not maybe very long experience, like as long as you trying to change anything in the system, it becomes pretty much more complicated. So, like at this moment, I would say that it's pretty tricky question, and well, maybe we need to have more time to discuss it because
yes, jet formation is very rich theory with a number of papers, mostly physicists, and I think this problem.
Did you work on it? Alternatively, Skubachevskii says that perhaps in 1 hour of discussion, we shall have possibility. No.
Immediately, I can tell you the following. In our, which was cited by Yulia Olegovna in our joint paper, we consider also another domain more complicated, torus.
Yeah.
And there, magnetic field has singularity at the axis x3.
Yeah.
But magnetic field, because inside torus, everything is okay. Second answer is the following. In my talk, I assumed at the beginning, and I underlined this, that local density can have singularity as 0 in spherical case. But we didn't consider this specially. I only reminded it for myself and for you. But in order to give correct answer to your question, it will be a pleasure for us to discuss this problem with you. Exactly. What kind of singularity do we want to have? What is the statement of problem? Assumptions concerning magnetic field, assumptions concerning distribution function, and so on.
Yes.
And possibly it can be done, something else.
It will be better.
But we didn't avoid this. In some
cases,
we meet this. Then also this problem arises in the construction of some nuclear reactors, because there is no such model like ball.
Yeah.
Because this is well-known geometric problem. I cannot translate it into English. Известный факт, как причесать ежа. It's impossible to have smooth, continuous and smooth magnetic field at the surface of sphere. You will have definitely singularity. Therefore, of course, it must be something, but we must understand your physical sense
yes.
problem in order to discuss. But for me, it will be interesting because this was this arised problem not only in our mind.
Let's discuss it separately. Yes.
Yes, separately.
Separately. Okay. It is an interesting problem. Okay.
Any other questions? We have a question from Jager. Please, Professor Jager. Professor Jager, sorry.
Sorry. Yulia, you said that you, by adjusting your magnetic field, you can keep the compact support. This sounds a little bit like control. Have you been looking at controls?
Well, it's not compact at all. I mean, we have our support inside the domain, but
inside,
yes. We cannot have fully compact. I mean, for the solutions that I mentioned, it's, I would say, in the pro. Equation to discuss and the points to look at.
Willy, first of all, good afternoon. Thank you for joining us. And second, let me tell you that from the beginning, I considered opportunity and also importance of consideration for this problem as control problem for systems with distributed parameters. But of course, there is no such complete theory. This is first remark. Second, I discussed this problem in Novosibirsk in nuclear Institute of Nuclear Physics named by Butcher. And they answered me that in reality, physicists, of course, maybe intuitively, maybe not, how to say, not like we should do it, but they consider this like control system, but only in the case of tokamak, because time of stability of plasma and time of plasma confinement is much longer in tokamak. In mirror trap, which considered Yulia in her talk, not in our joint paper, it were two models there, but in mirror trap, time of living of this high temperature plasma is equal to several milliseconds. And it's impossible to use feedback loop. This is the main obstacle. This is not realistic. But of course, we are thinking about it, and we hope to do this sooner or later. But it's very complicated, important, but very complicated problem. Control theory for reactors.
I understand that the main problem is controlling then the magnetic field. It's a technical problem because of time scales.
Thank you so much, Willy. Any other questions? Any other questions? Of course, I have a lot of questions to Yulia and Alexander Leonidovich, but I shall stop with my question. We have 1 minute for preparation of the next lecture. It is, thank you, Yulia, for a very interesting lecture. And is Mikhail Valerianovich here for his presidents? Okay. We can start. We can start now. Already we have a lecture of Professor Zaytsev, Peculiarity of Solutions of Laplace Equation as applied to the problem of describing the motion of a hydrodynamic discontinuity in a potential and incompressible flow in an external. Okay. Here everybody is professor. Don't pay attention.
А вот так дальше. Так, и как пользоваться? Сейчас вот туда и туда. Лазерная таска. Сейчас. Так, сюда. My report is based on the paper. This is such a name. Paper is journals. Yes, and we study this hydrodynamics discontinuities. This paper. Some new result. Consider propagation of hydrodynamic discontinuous surface. We assume that an external region is the region where the earlier equations are, and such a kind of compression that external flow is potential and compressible. That is why the u is velocity is expressed by a gradient of phi, and for phi we have Laplace equation which is following from the equation phi. Different divergence on the boundary, each point moves with the speed in minus Vn, where n is internal normal to the surface, and we assume that the velocity of planar erection front relative to stationary fuel is equal to unity, and that is why the surface relation with this takes this form, and I show we external for vorticity is 0. We consider the point M with which is moves with the velocity minus Vn in external region, and vector tau is tangential to the surface, and n is normal vector into the products of reaction. External flow where designate minus, and internal region which designate plus. Consider the Laplace equation for the velocity potential phi in two-dimensional region before the discontinuity phi. It is well known to consider the Laplace equation for derivative of phi on time, with respect to time. And we assume that approaching the flow, approaching the discontinuity is smooth enough with respect to coordinates time. The following is important assumption. And the following two relations on the surface, actually it is the well-known green relations on the surface. 7 is relation for the phi, 8 is a relation for the derivative of phi with respect to time t. I used the usual information from differential geometry. The relations on the surface, and we assume that smoothness and of the flow in coordinates and time using this. We have the following relations on the surface. This 11 and where dt is the derivative, full derivative of the points moving with the speed minus n. Yes, there are the usual the obvious relations. If we consider the coordinates tau and n on the front, we have this just auxiliary formulas. This also we now differentiate the green function with the time on the moving surface of discontinuity. Define the discontinuity in the form just x depending on t and y, until t на альфа, потому y is y of t and alpha. Alpha is interval from A, B, to every point with the speed minus v n. And we have the following relations from school. Differential geometry. We have such a formula, and it is just auxiliary relations. Using this definition of a curve, we can rewrite the ring for formula 7, the form just like this. Anyway, differentiate this formula with respect to time on moving points, and this check arises to such a complicated formula arises, and we return back to the coordinate r, usual coordinates, and have after differentiation such a additional relation, additional u relation on the front. Just too long formula, and impossible to exclude the derivative like this. And we actually have two equations, 24 and it depends on phi and d phi with respect to d and s, and just phi on the surface. Yes, some more form also equation, something more equation we can receive with differential with respect to coordinates x and y. For this, we consider the Laplace equation for coordinate for derivative of with respect to x and y of potential phi. For this, if from 25 and 26 equations, new form green functions relations on the surface can be described or can be seen in such a form. We use this obverse relations just after substituting these designations to formulas, we have the equations on the surface of discontinuity. At last, we have 1, 2, 3, 4 formulas on relations on discontinuities, which is actually the equations only for two unknowns. Just appendices for actually to derive these additional equations on the surface, we use the ring formula on the surface, and for the another equation, we can receive the new surface equations by using the ring formula of modification on the ring formula of these equations. We have, I don't show, there is, yes. What two? What just what тут was the info. Just it doesn't matter. We use only that for the heat transfer equations. We used that just equation before, and we use we transform this equation to Laplace equations, and through Laplace equation we can write the green formulas with such a this additional relation for the heat transfer equation. We have used this method. We hope can give additional surface equation for Poisson equation in 2D case of compressible form. We use we introduce additional functions, and for these functions we have two Laplace equations. And we have two Laplace equations. We have two green formulas. We also try to write this to show how to have additional green type formulas on the surface by for the system of differential equations of such a kind. This Laplace equation, this and this. We just there are some transformation. I will leave it for this report. Also can appendices D. We have this. We have identities of the green formula type. Just we consider the green formulas for phi with respect to dx, dx. We have the result. We have the following identity of if identity on the surface, at any surface that inside of domain of definition of Laplace. Yes, just the surface where the phi approaches the closure infinitely smooth, and we have the relation like this. We see that derivative with respect to x is goes out of integral. Just it is just identity for the two surface functions. Phi for Pn, phi RT of RT. Thank you very much.
Thank you very much for an interesting talk. Are there any questions to our lecturer? Then I have several questions. Please answer us. Can you summarize your results? Summarize some conclusion remarks that will show us the results.
Yes. In this paper, we in general have proposed a way to reduce the dimension in the Laplace equation using Green's formulas as additional equations. This is necessary to simplify and verify the calculation of this equation in the applications using reaction front as an example in 2D stream and over determined system of equations obtained that describe its motion in terms of the surface itself. It doesn't need the information is No, just information is needed from external flow, but it goes into equations through the boundary conditions for this integral equations on the surface. And assuming divisional smoothness of the harmonic flow approaching discontinuity, one can determine the motion of discontinuity without taking into account the influence of the flow behind front. But now I question about this, but I have some ideas how to solve this problem. As well as there is no physical explanation for this mechanism of movement of hydrodynamic discontinuity. It is possible that boundary layer of liquid is formed in the front where viscosity plays a significant role, and earlier equations are violated. Thus, the motion, the hydrodynamic discontinuity is smooth and potential and compression for external regions should be explained precisely. I think so, but maybe I'm incorrect. You just I've done what I could.
Thank you so much. Very interesting. Let us ask again. Are any questions to Professor Zaytsev? No questions. So let us thank him and give him a certificate. Here is Maxim Leonidovich. So there is not correct. There was signed as Mikhail. So here is more correct. That is great. Our organizing committee is on high level, and now we have 5 minutes break for our next lecture. Here is Yulia Olegovna Belyaeva to get certificate. our last lecture is the lecture of Professor Minenkov and Professor Votiakova from the Ishlinsky Institute for Problems in Mechanics. Asymptotics of one-dimensional shallow water equations in the form of running waves in a basin with a variable bottom with vertical and gentle walls. Please.
Good evening, everyone.
20 minutes. 20 minutes.
First of all, I'm so grateful for organizers for an opportunity to make a report today. I will present our joint work with Minenkov and Sergeyevich. The topic is asymptotics of the one-dimensional shallow water equations in the form of running waves in a basin with variable bottom with vertical and gentle. Problem statement. We consider the Cauchy problem for the one-dimensional shallow water equations. Here, mu is a small parameter responsible for the water length. Epsilon is wave amplitude, also small parameter. Eta it's wave surface elevation. U it's horizontal velocity. Eta and U with indexes, there are localized initial data, smooth functions decreasing at infinity. Due fixed at bottom depth function. We consider our problem in bounded domain. We consider two types of boundaries. The first type is variable boundary related with shore. It's set by the equation eta plus d equal to 0. The second type of boundaries is a vertical wall. On it, we set name and non-flow condition, horizontal velocity on the wall equal to 0. Motion of wave in our domain looks like localized initial data run up on the vertical wall, reflected from it, satisfying name and no-flow condition, run up on the shore, reflected, and so on. The main purpose of our work is to receive a formal asymptotic solution of the Cauchy problem. An interesting research goal is to investigate how the change in the wave profile is related to an increase in the Maslov index upon reflection from the wall. In our work, we consider two types of domains. The first is left shore and right wall, and the second is two shores model. Speaking about relevance of our work, from the physical point of view, the shallow water system describes the behavior of long waves. For example, tsunamis or stages. There are a big amount of works. For example, some references, Pelyanovsky and co-authors, Zaytsev, Stoker, and a lot of others. Secondly, the metamorphosis of the wave profile, wave shape, under the reflection of boundaries is studied. Is some work. We also have some references. And the last word is that asymptotics and exact solutions for various models of nonlinear shallow water are constructed by using special transforms of variables. Some references also presented. An important remark that there are some very recent works, for example, work of Chubunov, and this year publication of Dobrokhotov, Minenkov, and Zaytsev. In this work, authors proposed method that becomes the main in our work. It consists of two steps. First step is to construct asymptotics of linearized shallow water system with respect to water length tends to 0. That asymptotics constructed in the domain with fixed boundary by using modified Maslov's canonical operator. The second step is to apply the asymptotic Carrel-Greenspan transform to obtain asymptotics of the nonlinear shallow water system with respect to amplitude tends to 0. An important remark is the relation between small parameters. Nowadays, this question is open, but there is one hypothesis that for non-crushing, non-collapsing the wave, it's enough to set wave amplitude much less than squared water length. Speaking more about linearization of our system, we used to asymptotic Carrel-Greenspan transform. It's substitution of variables. As a result, our nonlinear system turned to a linear system with small, some small function in the right. We will call it linearized system. Without the right side, it will be a standard wave equation. The main idea, the main plus of this transform is that our variable boundary is fixing. In the nonlinear case, it's purple colored wave. Our solution is running on the bottom. In the linearized case, it's a yellow colored wave. Our wave propagated in fixed domain. In this case, it's vertical x. On the fixed boundary, we need to set some boundary condition. It is not correct to put Neyman or Dirichlet condition. Eilenik and Drankevich in their work proposed limited energy condition. It's some limitation for the norm. Next, I will say about geometric interpretation of the modified Maslow's canonical operator. To construct asymptotics of the linear system, we need to have closed Lagrangian manifold. But there are cases, a lot of cases, when solution of the Hamiltonian system gives us unclosed Lagrangian manifolds. For example, slope in bottom, d of x equal to x. In this case, we have such Lagrangian manifold with two types of singularities. The first type is near the shore, when momentum is plus minus infinity, and the second singularity is on the vertical wall. To construct a closed manifold, we map such pairs of points. And when we have this closed manifold, we can project a finite amplitude from upper sheet of manifold on the configuration space by the Maslow's canonical operator. And this way is applied to a wave equation, linear shallow water. To satisfy boundary condition on the vertical wall, we used a reflection method. The idea is that we put on the fake domain at the right of the wall wave that is a projection onto the configuration space, amplitude from lower sheet of manifold. It also corresponds to wave equation, and sum of real and fake waves need to satisfy condition on a vertical wall. To find parameters of the fake wave, we need to consider two types of indexes. The first is Maslow's path index. We can also name it index of a non-singular charge. And the second is index of a singular charge. The relation on the different sheets is presented. We find out that the increments on after reflection from the vertical wall is presented, and from the shore. We'll speak about the relation between these increments and changes in the wave profile. We considered two models. I will start with wall-plus-shore model. We considered two types of initial data. The first type is a running wave. It is the wave with non-zero initial velocity. In this case, we observe metamorphose from head to end wave after reflection from the shore, and symmetric reflection from the wall. This is corresponding to theoretical ideas presented in the work of Pilinovsky model. The second type of initial data is a piston model. It's a wave with zero initial velocity. In this case, solution is eigenfunction of Hilbert transform with eigenvalues plus minus 1. This type of metamorphosis of profile also corresponded to theory. This idea was studied in the work of Anikin and Minenkov. In the case of wall and shore, we can see 8 types of profile. In the same ideas were studied for two shores model. In this case, there are 4 types of wave profile. So we can conclude that our solution is a periodical function. period is equal to time for reflection from the shore. Next, I will present formulas that we received in our work. I will start with an important example, slope in bottom, d of x equal to x. In that case, we received a formal asymptotic solution for the nonlinear Neyman problem. This is formula for it. Here we used exact solution of the linear Neyman problem. It tells a new result for the model with vertical wall. It is formula for it. We constructed it by using a result of Dobrokhotov-Tirozzi. That is the exact solution of the linear Neyman problem without vertical wall. So we find increment of Maslov index and time shift. There is dynamic pixels illustrated reflection from the vertical wall in the lecture for the linear problem in the left and for non-linear problem on the right. In this situation, non-collapse condition, it is strictly condition of existence the transform, asymptotic Karel-Greenstein transform, Jacobian transform needs to be non-zero. Now I will speak about the general case. There are different formulas for wall plus shore and two shores model. There is formula for wall plus shore model. In this case, we used asymptotics of the linear problem. It's also new formula for this module. And for the two shores model, there is a piecewise function as a result. In this case, we used asymptotic solution of the wave equation, linearized shallow water. As a result, we have also dynamic pictures, illustrated reflection from the vertical wall and left shore in the left, and reflection from two shores in the right. All results for nonlinear problem. In this case, non-collapse condition is not strict. It is asymptotically a condition of existence of the transform. Also, it's asymptotically non-linear asymptotic condition for small parameters. That's everything. For linear problem with slope in bottom and wall, we received the exact solution in the form of localized wave in elementary function. For linear problem with an uneven bottom, for wall plus shore model, we received asymptotics presented in the form of localized wave in elementary functions. Both results used to solve a nonlinear problem. For nonlinear problem with slope in bottom and wall, we received a formal asymptotic solution in the form of localized wave. The theorem that is formal asymptotic solution proved in the work of Dobrokhotov, Minenkov, and Zaytsev. In a special case with initial conditions of special type, the answer is obtained in an elementary function. They are useful to realize on the computer. For nonlinear problem with an uneven bottom for a wall plus shore model and two shores, we received formulas to localized waves at the physical level. They need to be proved, not proved yet. And also the relation of the change of wave profile with increment of the Maslov index is investigated. Also, speaking about future plans, we need to prove a theorem for the formal asymptotic in the general case, and all this method can be applied for a two-dimensional shallow water system. There are references to the literature, and we are grateful to Sergei Yuryevich Dobrokhotov, Vladimir Evgenievich Zaytsev, and Andrei Igorevich Shvarevich for their support and valuable recommendations. That's all. Thank you very much for your attention.
Thank you very much. Who has any question to Maria Mikhailovna? Any questions? Could you show us the statement of the problem? Explain us some definitions. Yes, here is. what is eta wave surface elevation? What does it mean, wave surface elevation?
Length of, show this length. It's elevation, возвышение.
This is a wave, yes?
It is still one-dimensional wave.
One-dimensional. So this is one-dimensional function, dependent upon t, yes?
Yes, it's a localized finite function.
Yes. And finite, is it finite?
Finite.
Finite, yes. And it is finite all the time. This is the consequence of the equation.
The main idea of this work is to have as a result a localized waves. Our initial data are localized finite functions, and in both moments of time, our wave is localized as a finite function.
And are any questions to Maria Mikhailovna? Specify, please, the boundary condition on the
boundary condition on the left side is the main problem of this work. We can't understand how to send it, and because of it, we linearize our system to send a limited energy condition, and after that we can solve asymptotically this problem.
Yes, here is I think the boundary condition is written even. This is the boundary condition.
Boundary
yes.
Condition on the fixed boundary. On variable boundary, we can't set boundary condition. What?
No, this is equality. Eta plus d equals to 0. This is boundary condition?
Yes.
This is boundary condition.
It's the main idea that for it is. Можно по-русски ответить? В этом основная сложная задача, потому что подобные условия сложно запрограммировать на компьютере. И поэтому для численных методов этот результат может быть полезным, потому что, чтобы тестировать, правильно ли там написана схема или что-то подобное.
So this condition is very difficult for computing, for programming in computer. This equation is difficult for computing.
This type of condition is difficult. It's only limited energy condition.
This is you need not for this condition. I think you need any problem in computer. Computer doesn't feel such a kind of inequalities. Yes, I think so. Huh? For several years ago, the most popular problem was the problem of destruction of platina. So it is untranslatable. So this is a movement on dry and dry bottom, yes, dry bottom, dry bottom.
I can also, можно даже по-русски.
Можно.
В линейном случае, когда мы ставим условия конечности энергии, мы видим, что вот слева картинка, что волна себя ведет достаточно странным образом на берегу. Она резко возвышается, но что физически нереализуемо. И в этом тоже особенность условия, и конечности энергии, и всего. Получается, что физически вот линейная система, она не особо имеет смысл. Поэтому мы решаем нелинейную, но при этом используя результат линейности.
So for linear conditions, this is dx equals to x. Yes, this is a linear condition. Это вот линейные условия.
Left is linear problem and
del от x равнее x это линейный кондиция. Это линейный просто. Вот то, что написано у вас, да?
Это просто это для одного случая. Это просто функция одна. А линейно-нелинейная это задача. То есть у нас есть линейная система или нелинейная.
Ага. Но у вас есть исходно нелинейная задача.
Исходно нелинейная. И получены формулы для вот случая такой функции одна формального асимптотического решения для нелинейной задачи, а в случае в общем получены формулы на физическом уровне строгости, они не доказаны.
So this is a non-linear problem, and the solutions are obtained. But in difficult cases, we use linearization. Yes.
Yes.
About what do you linearize about? Вокруг чего вы линеаризуете?
Линеаризация в нашем случае это просто замена переменных, которая переводит, ну вот то, что я показывала. Существует оригинальная замена Керрила-Гринспена, которая переводит нелинейную задачу в строго линейную. То есть,
so there is such a linearization. How do we call it?
Kerril-Greenspan.
Kerril-Greenspan linearization that gives from nonlinear equations linear equations. Yes?
But in this case, we can't use origin Kerril-Greenspan transform because it is not fixed boundary. We used asymptotic Kerril-Greenspan transform proposed in the work of the Доброхотов, Minenkov, Zaytsev in this year.
I see. Okay. Are there any questions to Maria Mikhailovna? Then let us let us applaudize her, and we give her certificate. Maria Mikhailovna, this is yours. Thank you so much for your presence and for your attention. Our session is over.